Have you ever stopped to, really wonder what everything around us is actually made of? I mean, the air you're breathing right now, the books you might be studying from, even the phone or computer you're listening on. What are the absolute fundamental building blocks, and how do we even start figuring that out? Welcome to the Deep Dive. We're here to help you master the essential concepts you need for your academic studies and, crucially, for your competitive exams. Today, we're diving deep into atoms and molecules. It's a fascinating story, really. We'll look at how our understanding developed, right from ancient ideas about matter through to the chemical laws that form the foundation of chemistry, and finally, modern atomic theory. Our mission here is pretty straightforward. Cut through the complexity, pull out the key insights, define those critical terms, and really clarify the principles of atoms and molecules. We want you to walk away with a solid understanding, ready for those exams without feeling completely swamped. So let's get started. Okay, so if we go way, way back, the earliest thinkers trying to grasp what matter is, this invisible stuff making up everything, what were their initial ideas? How did they even conceive of dividing things down so far?
It's actually quite profound when you think about it, isn't it? This idea of an ultimate particle wasn't something new. Back in India, around 500 BC, you had Maharishi Kanad. He suggested that if you keep dividing padarth, that's matter, you'll eventually hit these tiny, tiny particles. He called them parmanu, indivisible, he thought.
Parmanu.
Okay. Yeah. And then another philosopher, Bakuda Katayama, built on that. He proposed that these parmanu usually don't exist alone, but in combined forms, which, explains why we see matter in different forms all around us.
Right, that makes sense. Not just single particles floating around.
Exactly. And interestingly, around the same time, over in ancient Greece, you had Democritus and Leucippus. They were thinking along very similar lines. They also argued that matter could be divided and divided until you reach these indivisible particles. Democritus actually coined the term atoms from the Greek word atomos, meaning uncuttable or indivisible.
Atoms. So the name itself comes from that ancient idea.
Precisely. But here's the really crucial point, especially when you're thinking about the history of science for your exams. These were philosophical ideas. Brilliant thoughts, yes, but purely based on reasoning, not experiments. There was no experimental proof back then. It was all, conceptual. It wasn't until the 18th century that scientists started doing experiments to actually test these ideas about matter. That shift from philosophy to experiment was massive.
That distinction is key, isn't it? From just thinking about it to actually testing it. So how did this new experimental era start to build the foundations of modern chemistry? Who were the pioneers there?
Well, this is where we meet Antoine Lavoisier and Joseph Proust. Their work, really meticulous experimental work, established two fundamental laws of chemical combination. These are absolutely essential for you to understand.
Okay, the foundational laws. What's the first one?
The first is the law of conservation of mass. Lavoisier is often credited with this. It states, quite simply, that mass is neither created nor destroyed in a chemical reaction.
So what you start with, mass-wise, is exactly what you end up with.
Exactly. The total mass of the reactants, the things you start the reaction with, equals the total mass of the products, the things you get at the end, always.
How did they demonstrate that back then?
A common way to show this, like in Activity 3.1 you might see in textbooks, involves, say, taking two solutions, maybe copper sulfate and sodium carbonate. You put one in a small tube inside a flask containing the other, seal the flask tightly with a cork, and weigh the whole setup very carefully.
Before mixing.
Before mixing, yes. Then you tilt the flask, mix the solutions, let the reaction happen. Maybe you see a precipitate form or gas bubbles. Then you weigh the sealed flask again after the reaction. And what you find is the mass hasn't changed at all. The cork is vital because it traps any gas produced, proving nothing was lost or gained.
That's a neat experiment. How might this appear in an exam question?
Good question. You might get something like this. In a reaction, 5.3 grams of sodium carbonate react with 6 grams of acetic acid. The products are 2.2 grams of carbon dioxide, 0.9 grams of water, and 8.2 grams of sodium acetate. Does this agree with the law of conservation of mass? To check, you just add up the reactant masses. 5.3 grams plus 6 grams gives you 11.3 grams.
All right.
Then add the product masses. 2.2 grams plus 0.9 grams plus 8.2 grams, that also gives 11.3 grams.
They match perfectly.
Exactly. So the data supports the law. You need to be comfortable with this kind of verification.
All right, that's conservation of mass. What was the second key law?
The second is the law of constant proportions, sometimes called the law of definite proportions. This was largely Proust's contribution. It states that in a chemical substance, the elements are always present in definite proportions by mass.
Meaning the recipe is always fixed.
Precisely. Take water, H2O, Doesn't matter if it's from a river, the sea, or made in a lab, the ratio of the mass of hydrogen to the mass of oxygen is always 1 to 8.
Always 1.8 by mass. Always. If you take 9 grams of water and break it down, you'll get exactly 1 gram of hydrogen and 8 grams of oxygen every single time. Or look at ammonia, NH3. The ratio of nitrogen to hydrogen by mass is always 14:3. Doesn't matter where the ammonia comes from, this fixed composition is fundamental.
How is this law typically tested?
You might see a calculation like, hydrogen and oxygen combine in the ratio 1.8 by mass to form water. What mass of oxygen gas is needed to react completely with 3 grams of hydrogen gas?
Okay, so if it's 1 gram of hydrogen needs 8 grams of oxygen,
Then 3 grams of hydrogen would need, well, you just multiply. 3 times 8.
24 grams.
Exactly, 24 grams of oxygen. It's a direct proportional relationship based on that fixed mass ratio. You need to be able to apply these ratios.
Got it. So these two laws, conservation of mass and constant proportions, really set the stage quantitatively. They described how things combined, but they didn't fully explain the why, right, or what was actually combining.
That's the perfect lead-in to the next major figure, John Dalton. His atomic theory was the breakthrough that provided the explanation. Right, Dalton. Tell us about him and his theory. It sounds like a real turning point.
It absolutely was.
Yeah.
John Dalton, born in England in 1766, came from a poor background. Amazingly, he started teaching at age 12.
12?
Yes.
Yeah.
He eventually became a respected teacher and scientist. In 1808, he presented his atomic theory, and it really revolutionized the study of matter. Dalton took that old philosophical idea of atoms, the indivisible particles, but he gave it a proper scientific basis. He connected the idea of atoms directly to the laws of chemical combination that Lavoisier and Proust had established.
So he provided the underlying structure, the model.
Exactly. He proposed a set of postulates. These are crucial for you to know. Let's go through them. First, all matter is made of very tiny particles called atoms, and these atoms participate in chemical reactions. Simple start.
Okay.
Second, atoms are indivisible particles, which cannot be created or destroyed in a chemical reaction. Now, this postulate directly explains the law of conservation of mass, doesn't it? If atoms are just rearranged, not created or destroyed, the total mass must stay the same.
I see the connection.
Clever. Third, atoms of a given element are identical in mass and chemical property. So all oxygen atoms are alike, all iron atoms are alike, and so on. Fourth, atoms of different elements have different masses and chemical properties. An oxygen atom is fundamentally different from an iron atom.
Makes sense. Different building blocks.
Fifth, atoms combine in the ratio of small whole numbers to form compounds. You don't get half an atom joining in. It's always 1.1, 1.2, 2.3, simple whole number ratios. And sixth, the relative number and kinds of atoms are constant in a given compound.
And postulates 5 and 6, they explain the law of constant proportions, right? If the atoms combine in fixed whole number ratios, the mass proportions must also be fixed.
Precisely. Dalton's theory provided a beautiful, logical explanation for both foundational laws. It was incredibly powerful.
It really is remarkable. If he couldn't see these atoms, nobody could back then, yet his theory explains so much about how chemistry worked, and now we can actually see them.
Well, not with our eyes, but yes, with modern techniques like scanning tunneling microscopy, we can get these incredible images showing surfaces structured atom by atom. It confirmed his basic idea, even if we now know atoms aren't truly indivisible.
So atoms are the building blocks, like bricks for a wall.
That's a great analogy. Or like tiny grains of sand making up an anthill. Atoms are the fundamental units that make up all the matter around us.
Just how tiny are we talking? You mentioned indivisible, but what's the scale?
Almost unimaginably small. Millions of atoms stacked up would barely be as thick as a sheet of paper.
Wow.
We measure atomic sizes in nanometers. Atom, 1 nanometer is 1/1000th of a meter, so 1 meter is 10 to the power of 9 millimeter. A single hydrogen atom is about 10 to the power of -10 meters across. A water molecule, which is H2O, is a bit larger, around 10 to 9 meters or 1 nanometer.
So tiny, which directly answers that common question, why can't we see atoms with the naked eye?
Exactly. They're just far, far too small for our eyes or even standard microscopes to resolve individually.
Okay, so they exist. They're incredibly small. How did scientists go about naming and symbolizing them consistently, especially with new elements being discovered?
Well, Dalton himself used pictorial symbols initially, but they were a bit cumbersome.
Like little drawings.
Sort of, yeah. Then a chemist named Berzelius suggested using letters from the element's name. That was much more practical. And today, there's an international body, IUPAC, the International Union of Pure and Applied Chemistry. They're the authority that approves the names, symbols, and units used worldwide in chemistry. It ensures everyone is speaking the same chemical language.
And there are rules for the symbols.
Yes, simple but strict rules you need to follow. The symbol is usually one or two letters. The first letter is always uppercase. If there's a second letter, it's always lowercase.
Like aluminium is al, not al, and cobalt is co, not co.
Precisely. Sometimes the second letter isn't the second letter of the name, like chlorine is Cl or zinc is Zn. And some symbols come from older names, often Latin or Greek, like iron is Fe from ferrum. Sodium is Na from natrium. Potassium is K from kalium. You just have to learn these common ones.
Right, learn the symbols. Now, what about their mass? Dalton said different elements have different masses. How did they figure out the mass of something so tiny?
That was a major challenge. Measuring the absolute mass of a single atom was impossible back then. So they cleverly figured out relative atomic masses.
Relative. Compared to what?
They used the laws of chemical combination. By carefully analyzing how much of one element combined with another, they could determine their mass ratio. Initially, they tried using hydrogen as a standard, then oxygen. For a while, 116th of the mass of an oxygen atom was the reference unit. Oxygen was useful because it reacts with lots of things and it gave masses that were often close to whole numbers.
But that changed.
Yes. In 1961, a universal standard was agreed upon. The carbon-12 isotope. The atomic mass unit, symbol U, which stands for Unified Atomic Mass Unit, is defined as exactly 1/12 the mass of one atom of carbon-12.
Okay, so everything is compared to 112th of a carbon-12 atom.
Precisely. It's like deciding a standard watermelon weighs 12 units, cutting it into 12 equal pieces, and then weighing all other fruits relative to one of those pieces.
Yeah.
The relative atomic mass of an element is its average atomic mass compared to that 112th C12 standard.
So if an exam asks, define the atomic mass unit, the answer involves carbon-12.
Absolutely. 112th the mass of one carbon-12 atom. That's the definition you need. And it's important to remember, as we touched on, most atoms don't just hang around by themselves. They're usually too reactive.
Right, they combine.
They combine to form more stable things, molecules and ions. And it's these molecules and ions gathering in huge numbers that make up the substances we actually see and touch.
Okay, perfect transition. So atoms combine. Let's talk about these combinations. What exactly is a molecule?
A molecule is, generally speaking, a group of two or more atoms that are chemically bonded together. They're held tightly by attractive forces. Crucially, a molecule is the smallest particle of an element or a compound that is capable of independent existence and shows all the properties of that substance.
Can molecules be made of just one type of atom?
Yes, those are molecules of elements. For example, some elements like helium, He, or argon, RR, exist as single atoms. We call them monoatomic. They're stable on their own. But many nonmetals form molecules with two or more identical atoms bonded together. Oxygen in the air is O2 oxygen atoms. It's diatomic.
Like hydrogen H2, nitrogen N2 as well?
Exactly. Hydrogen, nitrogen, chlorine, Cl2 are all diatomic. Ozone is O3, 3 oxygen atoms, so it's triatomic. Phosphorus often exists as P4, tetraatomic. Sulfur can be S8, which we call polyatomic. This number of atoms in a molecule is called its atomicity.
Atomicity, got it. What about metals?
Metals and also carbon in forms like diamond or graphite don't really form simple discrete molecules. They have large sort of indefinite networks of atoms bonded together.
Okay, so that covers molecules of elements. What about molecules of compounds?
Molecules of compounds form when atoms of different elements join together chemically, and crucially, they do so in definite, fixed proportions. Remember the law of constant proportions.
Right, like water H2O, always 1.8 by mass.
Exactly. Or ammonia NH3, always 14.3 nitrogen to hydrogen by mass. Carbon dioxide CO2, always 3.8 carbon to oxygen by mass. The composition is fixed.
You mentioned earlier we can figure out the ratio of atoms from the mass ratio. Can we walk through that again? It seems important for calculations.
Yes, absolutely critical. Let's use water H2 again. Mass ratio HO is 1.8. Atomic mass of H is 1U, O is 16U. To find the ratio of number of atoms, you divide the mass ratio by the atomic mass for each element. So for H, its mass ratio atomic mass equals 1 equals 1. For O, its mass ratio atomic mass, H16 equals 0.5 or 12.
So the ratio is 1 to 0.5. That doesn't look like H2O.
Right, we need simple whole numbers for the formula. So we convert this ratio 1.5 into the simplest whole number ratio. We can do that by dividing by the smallest number, 0.5, or often easier, multiplying both by a number to clear the fraction. If we multiply both 1 and 0.5 by 2,
you get 2 and 1.
Exactly. So the ratio of hydrogen atoms to oxygen atoms is 2.1. That gives it the formula H2O. You absolutely need to practice this conversion from mass ratio to atom ratio using atomic masses. It comes up a lot.
That's very clear, thanks. Now, compounds aren't always neutral molecules, are they? You mentioned ions earlier.
Correct. Especially compounds formed between metals and nonmetals often consist of charged particles called ions. An ion is basically an atom, or sometimes a group of atoms, that has gained or lost electrons, giving it an overall positive or negative charge.
Positive and negative ions, cations and anions.
Yes. Positively charged ions are cations, like Na plus sodium ion. Negatively charged ions are anions, like Cl, chloride ion. Tail salt, NaCl, is made of these ions, Na plus and Cl. Sometimes a whole group of atoms can carry a charge. These are called polyatomic ions.
Like the ones you see in tables. Ammonium, sulfate.
Exactly. Ammonium is NH4 plus kyne, hydroxide is OH, sulfate is SO42, carbonate is CO3D2. You need to be familiar with the common ones and their charges to write formulae correctly.
Which brings us neatly to writing chemical formulae. This seems like a place where mistakes can easily happen in exams if you're not careful. How do we get it right?
It comes down to understanding valency. Valency is basically the combining capacity of an element. Think of it like the number of arms an atom uses to bond with others.
Arms, like the octopus analogy you mentioned.
Yes, that analogy works well. If an octopus O has 8 arms, valency 8, though oxygen's is usually 2, and a human, H, has 2 arms, valency 1 for H usually, how do they hold hands? The octopus needs to hold 4 humans, OH4 in that specific analogy, to use all its arms, assuming each human uses 1 arm per octopus arm. In real chemistry, the valencies need to balance out. There are clear rules for writing formulae. Rule 1. The valencies, or the charges on the ions, must balance. The overall compound must be electrically neutral.
Okay, total positive charge must equal total negative charge.
Exactly. Rule 2. When writing the formula for a compound with a metal and a nonmetal, the symbol of the metal always comes first. So calcium oxide is CaO, not OKa. Sodium chloride is NaCl, not KLNa. Metal first. Got it. Rule 3. If your compound contains a polyatomic ion, and you need more than one of that ion to balance the charges, you must put the ion's formula in parentheses, brackets, and write the number needed as a subscript outside the bracket.
Brackets for multiple polyatomic ions. Example.
Magnesium hydroxide. Magnesium ion is Mg2+, hydroxide ion is OH. To balance the 2+ charge of magnesium, you need 2 hydroxide ions. So the formula is MgOH2. The brackets show the 2 applies to both the O and the H in the hydroxide group.
What if you only need 1 polyatomic ion?
Then no brackets. Like sodium hydroxide, Na plus and OH. Charges balance 1.1, so just NaOH.
Okay, let's try applying these rules. How about, say, aluminium oxide?
Right. Aluminium Al is typically valency 3 forms Al3+. Oxygen O is valency 2 forms O2. We need to balance the charges. The simplest way is the crisscross method for binary compounds. Write the symbols. Al-O, write the valencies above them, 3 for Al, 2 for O. Then crisscross these numbers as subscripts, ignoring the charge signs. Al gets the 2 from oxygen, O gets the 3 from aluminium.
So Al2O3.
Perfect.
Al2O3.
Let's try calcium oxide. Cal valency 2, O valency 2.
Crisscross gives K2O2.
But remember rule 1 about balancing and simplicity. If the valencies are the same, or have a common factor, you simplify the ratio. Since both are 2, the simplest ratio is 1.1, such as CaO.
Okay, simplify when possible. How about sodium nitrate?
Sodium is Nap plus MAP, valency 1. Nitrate is the polyatomic ion NO3, charge -1, so valency 1. Charges balance 1.1.
So NaNO3, no brackets needed.
Correct. One more complex one. Ammonium sulfate. Ammonium is NH4 plus air, charge +1. Sulfate is SO42, charge -2. To balance the nanoU charge of sulfate, you need 2 + 1 ammonium ions.
2 ammonium, so we need brackets around NH4.
Yes. You write it as NH4 2SO4. The brackets show there are 2 NH4 groups for every 1 SO4 group. Mastering these rules and practicing with examples from your textbook exercises is absolutely key.
The systematic approach definitely helps. Okay, final quantitative step. Calculating masses. Once we have the correct formula, how do we find the molecular mass or the formula unit mass?
It's quite straightforward once you have the formula and know the atomic masses of the elements involved. Molecular mass applies to substances that exist as discrete molecules. It's simply the sum of the atomic masses of all the atoms in one molecule of that substance. Units are atomic mass units.
The example, water, H2O.
Right. Atomic mass H is 1EO, is H2, formula is H2O.
Oh.
So molecular mass 2 atomic mass of H plus 1 atomic mass of O plus 1 that's 16U plus 1 I give 16U plus 16U plus 16U plus 8.
Okay, how about nitric acid, HNO3?
H1U, O6 in U, formula HNO3. So mass 1H1U plus 1I14U plus 3, 1 plus 14U plus 48 is 63U. You really need to practice calculating these for common molecules like CO2, CH4, NH3, etc., as listed in your exercise. It's a fundamental skill.
And formula unit mass. You said it's similar but for ionic compounds.
Exactly. The calculation method is identical sum of atomic masses of all atoms in the formula unit. We just use the term formula unit mass because ionic compounds don't form discrete molecules, but rather a crystal lattice represented by the simplest formula unit.
Like sodium chloride, NaCl.
Yes. Atomic mass Na, 23U, Cl equals 35.5U. Formula unit is NaCl. So formula unit mass, a 1I23U plus 1I35.5U equals 58.5U.
I am calcium chloride, KCl2, NCl, Cl equals 35.5U. Formula unit KCl2 mass, or 1.40U plus 30 plus 71 equals 111DO. Again, practice with examples like ZNO and A2O, K2CO3 from your textbook questions is crucial for exam speed and accuracy.
Absolutely. These calculations form the basis of stoichiometry and so much more in chemistry. They're essential tools. Wow, we've really covered a lot of ground today. From those very first philosophical ideas about matter being divisible,
All the way through the fundamental laws of chemical combination.
to Dalton's brilliant atomic theory that explained those laws.
And then understanding atoms themselves, their size, symbols, mass, followed by how they combine into molecules and ions.
And finally, how to write their formula and calculate their masses.
It truly is the foundation, isn't it? These concepts underpin so much of chemistry, essential knowledge for all students preparing for exams.
Without a doubt. Getting these fundamentals right, the definitions, the laws, the postulates, the calculations, gives you such a strong base to build upon for more advanced topics. I really encourage you to go back, review these concepts, practice the examples. They come up again and again.
Definitely solid advice. And as we wrap up this deep dive, here's something to think about. Dalton's theory was revolutionary, proposing atoms as indivisible. But science didn't stop there. What discoveries came later that showed atoms themselves have an internal structure, that they aren't the fundamental indivisible particles after all? That discovery opened up a whole new level of understanding matter, something to explore as you continue learning. Stay tuned for more exam-ready insights and in-depth topic breakdowns. Subscribe to the Deep Dive so you never miss a crucial lesson. In this deep dive, we covered the following topics: ancient ideas of matter divisibility, laws of chemical combination, conservation of mass in constant proportions, Dalton's atomic theory and its postulates, understanding atoms, their size and symbols, atomic mass and the carbon-12 standard, molecules of elements and compounds including atomicity, ions, cations, anions, and polyatomic ions, the rules for writing chemical formulae using valency, and finally, calculating molecular mass and formula unit mass.